During the Gulf War, helicopter engines were failing not from combat damage, but from the air itself. Desert sand was entering turbines and triggering a failure mode most engineers hadn't fully anticipated. At operating temperature, silica sand melts into glass. That glass coats the blade cooling channels, blocks airflow, and destroys the engine in under 30 minutes. Replacement cycles that normally span thousands of flight hours collapsed to dozens. Aircraft were being grounded faster than engines could be flown in. The engineering response was a device that spins incoming air into a vortex before it reaches the turbine. No filters, no moving parts. During the Gulf War, the U.S. Army tracked a problem that had no straightforward fix. And helicopter engines, specifically the turboshaft engines powering the Black Hawks and Apaches operating over Iraqi desert, were failing at rates that had no precedent in the maintenance records. The engines weren't being hit. They weren't suffering mechanical failures in any conventional sense. They were being destroyed from the inside by the air they were breathing. Desert air in that region carries fine silica particles suspended at concentrations that ground-level visibility metrics don't fully capture. A helicopter operating at low altitude in disturbed desert conditions, landing, hovering, conducting nap-of-the-earth flight, pulls that particulate-laden air directly into its intake at high volume. The engine requires large, continuous airflow to sustain combustion. That requirement doesn't change because the air is dirty. The failure mode wasn't what most engineers initially expected. Sand ingestion in turbines is commonly associated with abrasion, particles physically eroding blade edges over time, gradually degrading performance across hundreds of flight hours. That does happen. But in desert combat conditions, the primary failure mechanism was faster and more complete. The combustion chamber of a turboshaft engine operates at temperatures above 1,300 degrees Celsius. Silica sand melts at approximately 1,600 degrees Celsius. Those temperatures are close enough that fine silica particles, small enough to travel deep into the engine before being combusted, reach partial or full melting point inside the hot section. Molten silica doesn't exit with the exhaust. It adheres to whatever surface it contacts first. Inside a turbine, those surfaces are the blade cooling passages, the small internal channels that circulate cooling air to prevent the blades themselves from exceeding their material temperature limits. When those passages coat with glass, cooling airflow stops. Blade temperatures spike. The engine fails, often within minutes of the process beginning. This is not gradual degradation. It is acute, chemistry-driven destruction. An engine that was fully functional at the start of a sortie could be unrecoverable by the end of it. The operational consequence was severe. Engine time. Between overhaul, the standard metric for turbine service life, collapsed from several thousand flight hours under normal operating conditions to figures in the dozens in high-particulate desert environments. Aircraft availability dropped. Maintenance pipelines were overwhelmed. Engines were being consumed faster than the supply chain could replace them. This was not a marginal degradation in fleet readiness. It was a systemic operational problem. The instinctive engineering response was filtration. Place a filter at the engine intake with sufficient particle retention to block the fine silica particles responsible for the glass formation failure mode. This is a solved problem in other domains: industrial air handling, HVAC systems, diesel engines, and the principle is well understood. But on a helicopter turbine at operational power, it fails for a reason that creates a genuine design contradiction. A turboshaft engine at full output requires a specific volume of airflow to sustain the combustion process. Any restriction at the intake reduces that volume. A filter with particle retention fine enough to catch silica sand, particles in the range of 20 to 200 microns, creates sufficient pressure drop across the intake to reduce airflow below the threshold the engine needs to maintain power. The filter that solves the sand problem creates an airflow problem severe enough to be its own failure mode. In combat conditions, reduced power availability is not an acceptable trade-off. The aircraft needs full output on demand. A filter that compromises that capability is operationally unusable regardless of how well it handles sand. The solution, then, could not restrict airflow. It had to remove particles from the incoming air without creating any meaningful resistance to airflow volume. Those two requirements, high particle removal efficiency and near-zero pressure drop, are in direct tension with each other in conventional filtration. Meeting both simultaneously required abandoning filtration entirely as the engineering category. What engineers developed instead doesn't filter the air at all. It doesn't capture particles, retain them, or block their path. It redirects them. The centrifugal particle separator uses the geometry of its intake tubes to generate a vortex, a controlled rotational airflow, through which all incoming air passes before reaching the engine. What happens to sand inside that vortex is governed entirely by physics, not by any filter medium. And the device that generates it contains no moving parts whatsoever. The separator removes the vast majority of what comes in, but not everything. Engineers defined a specific particle size below which they were willing to accept pass-through, and the reasoning behind that threshold is more precise than it first appears. The centrifugal particle separator works on a single physical principle. In a rotating flow, denser objects migrate outward. That principle requires no mechanical input to operate. It requires only the right geometry. Each separator consists of a set of tubes, typically arranged in a parallel bank across the engine intake cross-section, through which all incoming air must pass. The interior of each tube is shaped to impart rotation to the airflow entering it. Inlet vanes or a helical internal geometry force the air into a spinning column as it travels through the tube. That spinning column is the vortex. It is generated entirely by the shape of the passage. No fan creates it. No motor sustains it. The airflow itself, moving through a correctly shaped tube, produces the rotation. Once the air is spinning, the separation occurs automatically. Air molecules and sand particles enter the vortex together, but they don't behave the same way inside it. Sand particles, silica, with a density roughly 2.6 times that of air, experience centrifugal force proportional to their mass. In a rotating flow, that force pushes them outward toward the tube wall. The lighter air continues to rotate near the center of the tube and exits through the inner outlet toward the engine. The sand, now concentrated at the outer wall, reaches a scavenge port, an opening in the tube wall connected to a separate exhaust path, and is ejected from the system entirely. The engine receives the air. The sand goes elsewhere. The separation happens continuously, in real time, with no component changing state. There is nothing to clog, nothing to replace, nothing to service after each flight. The geometry that creates the vortex is fixed. As long as air flows through the tube, separation occurs. Particle removal efficiency in operational centrifugal separators typically falls between 90 and 95% by mass. That figure is not 100%, and the gap is not an oversight. The particles that pass through the separator are the finest ones, those with the least mass and therefore the least response to centrifugal force. In a vortex with a given rotational speed, there is a particle size below which centrifugal separation force becomes insufficient to migrate the particle to the outer wall before it exits the tube. Those particles continue to the engine. Engineers accepted this because of what those fine particles actually do inside a turbine. The glass formation failure mode, the mechanism responsible for the acute engine destruction observed in desert operations, requires particles large enough to reach the blade cooling passages and accumulate as a blocking deposit. Fine particles below a certain diameter pass through those same passages without lodging. The cooling channel geometry that makes large particles catastrophic makes fine particles tolerable. The threshold was calculated, not guessed. Engineers defined the separator's effective cut size to target the particle range responsible for the critical failure mode, accepting pass-through of the range that posed manageable risk. The device added length to the engine intake assembly and introduced a minor pressure drop, smaller than any filter capable of comparable particle retention, but not zero. That trade-off was accepted across every platform on which the separator was adopted, including the Black Hawk and Apache fleets that identified the problem most acutely during Gulf War operations. The performance data from those platforms and from subsequent operations in Afghanistan and Iraq validated the approach. Engine TBO figures in high particulate environments recovered substantially compared to unprotected operation. The same tube geometry that protected helicopter engines in the Gulf War now appears inside power stations across the Arabian Peninsula, doing the same job at 10 times the scale. Industrial gas turbines used for power generation in desert environments face an identical problem. Fine silica in the intake air, combustion temperatures sufficient to produce glass formation damage, and airflow requirements that make conventional filtration impractical at the volumes involved. Centrifugal separation at the industrial scale uses the same vortex tube principle, scaled to intake dimensions measured in meters rather than centimeters. Offshore gas platforms, pipeline compressor stations, and desert power facilities on multiple continents now operate turbines protected by direct descendants of the helicopter intake separator. The problem that emerged from desert combat operations turned out not to be specific to helicopters or to military use or to any particular scale of turbine. It was a physics problem. Rotating flow separates particles by density. That relationship holds at any scale in any application, wherever a turbine must breathe contaminated air. The device didn't filter the problem out. It spun it away.